Then we'll move to our next speaker, Teresa Valdivia Mena. If you can start sharing your screen.
Okay, so can you see the mouse?
Yes, and the screen is full screen, so this all looks good. So our next speaker will be Teresa Valdivia Mena, my apologies, who will talk about rivers in the sky. I'm curious about what that is. Streamers discovered towards 2 class 1 sources in Perseus. Please go ahead.
So thank you for the nice opportunity to give this talk. So yes, well, my name is Maria Teresa, but I usually only use the name Teresa just because it's easier. So I'm a second-year PhD student at the Max Planck Institute for Extraterrestrial Physics. I work in the group of Paola Caselli. And today I'm actually going to pull you back to the galaxy, and where I want to talk about 2 streamers that we've discovered towards class 1 sources in the molecular cloud of Perseus. So one of the areas that has been revolutionized by the presence, by the use of ALMA, has been low mass star formation. In particular, one of the first results that was highlighted very heavily in the news was the discovery of rings and gaps in the dust continuum of HL Tau, and from this image from the cycle 0. So my research is focused on the physical and chemical properties of young stellar objects that are still embedded within their natal cores. So for us to be on the same page, on the left, I show an amazing infrared picture of NGC 1333, which is part of the molecular cloud of Perseus in our galaxy. And to the right is the current understanding, the classical picture of star formation. There are 3 classes that I want to focus on, which are class 0, 1, and 2, which are defined by their spectral energy distributions, and in theory represent this part of the scheme, which is an evolutionary sequence. So we start from a prestellar core, and then when the young stellar object is formed, at first we cannot see it, and this is what we call the class 0 phase, where it's completely veiled by its envelope and surrounding material. And when it's starting to get unveiled and we can actually see it, although there's a lot of material still, we call it the class 1. And when it starts to be almost completely unveiled, and we can see this protostar and protoplanetary disk, that's when we call it class 2. And this is where more or less the HL Tau image is located. Now, this is usually veiled in very dense gas that we usually see in ammonia. So this picture has 2 assumptions that are quite problematic. One is that the cores are isolated, and that there is axisymmetry in all of this process of accretion. And simulations systematically find that this star formation is not axisymmetric at all. Basically, similar to very other processes at larger scales in our galaxy and other galaxies, they systematically find this asymmetric structures at all scales. So I focused on the scales of several thousands of AU to several hundreds of AU. So if we zoom into the cores of the simulations, we see these filamentary structures that we call streamers, which are usually 20 to 30,000 AU or even longer. And that if we zoom into the individual cores, we can see that they can reach down to even the disk scale. So a few hundred AUs or even less. So there has been a recent boom in the discovery of streamers in actual observations that were predicted from the simulations. This has been in the last 4 to 5 years, I would say. So streamers have been found in all classes that I mentioned before, from the highly veiled class 0 to the unveiled class 2. And I want to highlight that these 3 works from Pineda, Segura Cox, and Alves, 2 of these are made by ALMA, and this is made by Noema. All of them interferometers, by the way. So the lengths vary mostly from class to class, although there are not enough streamers to make a statistical analysis of this. There must be 10 or even less. So the longest one is in a class 0 by Pineda et al. 2020. This is in Perm 2 in Perseus as well, which has a length of around 11,000 AU. And the ones that we have observed in class 1 and in class 2 are usually shorter, but as I will argue, it is probable that these are actually very much longer. Now, it is unclear how these streamers actually affect the evolution of the protostar and the protostellar disk. And in particular, I'm interested in how they affect the class 1 sources. So here, for example, I show IRS 63, which is in Ophiuchus, if I'm not mistaken. And with ALMA, we can see in Segura Cox et al. This beautiful streamer that lands towards the disk or pseudo disk region, but it's not really clear how it affects the disk. And to highlight the relevance of these objects, even in HL tau, like the famous HL tau class 2 source, we can actually see a hint of a streamer landing towards this disk scales. By the way, also found with ALMA, published recently this year. So I studied the surroundings of 2 class 1 protostars, both in the Perseus molecular cloud, which is around 300 parsecs from us. So this is a beautiful image on the optical range where we can see the obscuration by dust and several OB protostars being formed. This is a molecular cloud that has several regions of star formation. So first I want to focus on NGC 1333, which is known as an active star formation region. And the protostar that I see here is Perseus, which is a class 1 protostar characterized by being about 10 times more luminous than the other class 1 sources surrounding it. Here we see an image of NGC 1333. Perseus is located about in this little finger right here. And all of these knots are dense gas cores and filaments seen in ammonia, which is a dense gas tracer. And here we know that in Perseus we have a very large disk, about 40 to 50 AU in size, in the VLA data in 8 millimeters dust continuum. And it has a whooping mass of about half a solar mass, which is a lot for us for a class 1 disk. But we didn't know what was surrounding this protostellar disk until we observed it with NOEMA, where we discovered a streamer with an approximate length of 3000 AU in H2CO emission, which is formaldehyde, if I'm not mistaken. Being in an astrochemistry group is hard when you're not a chemist. So the tip of this streamer, until what we can characterize, is actually just at the primary beam edge. And there is emission outside of this primary beam edge, which we can unfortunately not characterize. So we consider the length of the streamer as a lower limit. And the streamer is unaffected by the outflow mostly because it's completely perpendicular to it. Here we see an image of a 12CO where we can see actually the outflows from Stevens et al. 2019. And we see that it's completely parallel to it. But does that mean that it is actually an infill motion? How do we make sure that it's an infill motion? So first we obtain the central velocities at each position of the streamer using a Gaussian fit. And these are actually very well fitted by a Gaussian shape. So here we see these velocities in the image plane, and here we see a kernel density estimation of the velocities within this polygon, where we define the streamer to be. And we see a clear gradient towards blue shifted velocities towards the inner 1000 AU from of the streamer towards the protostellar disk. And it's roughly constant along the outer 1000 AU, except for this kink right here. Now, what we did was see the analytical solutions of a parcel of mass free falling from a rotating sphere from Mendoza et al. And we could find parameters that adjusted to this velocity that we see. And they agree very well with these velocities when we add a little initial velocity of around 1.2 kilometers per second at the beginning of this streamer. This actually hints that the streamer can actually begin further away than what we can see. And it also confirms that this material is in free fall. Now, a natural follow-up question is how much mass does this asymmetric infill transport towards the protostellar disk? Fortunately, we also had C18O observations with NOEMA, and we showed that there is streamer emission in C18O. However, there is also larger scale emission that we cannot recover fully because we're missing the zero scales. So we measured a lower limit to the mass, lower limit because of the length of the streamer and because of the missing scales. And we found that the info rate varies very little with the distance with respect to the protostar, using also the combination between the mass that we obtained and the streamline model. And we found that the info rate, which is the mass transported from the streamer to the disk, is about 10 to the minus 6 solar masses per year. This value is about 5 to 10 times the accretion rates estimated from infrared spectra by Fiorellino et al. In 2021. So what we think is happening is that the streamer helps to accumulate mass in the protostellar disk, and that will in the future probably produce a very strong accretion burst. Now we move to a more quiescent region where I observed another protostar. This is Barnard 5. And I must note that everything I will show right now is completely preliminary. So the protostar here is called IRS-1. And here we investigate both the large scales of the filaments and condensations, and as well as the inner 3000 AU from the class 1 protostar. Here we see two beautiful filaments and 3 condensations together with IRS-1, seen in dense gas in ammonia from BLA observations by Pineda et al. 2015. So these 3 condensations and the protostar are thought to form a quadruple system as they are gravitationally bound. So looking at a less dense gas tracer, but a chemically fresh gas, we see in HC3N with Noema and iron that we have the same shape as in dense gas. However, there is more extended gas emission. And also we observe with ALMA that there's this beautiful butterfly outflow, with almost 90 degrees of aperture, which indicates more than it's a class 1, perpendicular to the direction of the filaments in this position. Now, if we compare the motions of HC3N and ammonia, we see that this chemically fresh gas is systematically redshifted, in particular in the regions of the condensations towards this filament. We interpret this as chemically fresh gas collapsing towards the filament and following its motion towards the condensations and the protostellar system. And here we see that it's blue shifted, but we need not to be worried about this because as it is a protostar, there's a lot going on here. There's outflows, there's inflow motions, and we need to look further, zooming in with higher resolution. And this is where ALMA actually comes in. If we zoom into this region, how many minutes?
3.
Okay, thank you. So if we zoom into this region, we see that there is axisymmetric gas towards PERM53 or IRS-1. And we see, zooming into with VLA, we see that there is an unresolved disk in this region. So here ALMA allows us to characterize this axisymmetric gas flow towards these scales. I will argue that actually this doesn't look like a streamer, but it is actually a streamer because we see evidence of free falling gas as well. So we do the same, we obtain also the central velocity using a Gaussian fit. And the whole you see here is because the velocity dispersion of the Gaussian fits here started to get supersonic, which indicated other motions like effects of the outflow, for example, or effects of rotation, which is a more ordered motion. However, the velocity dispersion here is subsonic, which indicates, and very thin actually, which indicates that it's not affected by the outflow, even though they share the same region in space visually in the image plane. So again, we looked at analytic solutions from an infalling mass, and here we find solutions that can describe this blue shift towards the protostar, although we are still testing solutions, so there can be a whole family of solutions here. This is only one, but there can be a whole family of solutions that describe both in the image plane and in the line of sight velocities. So we are still testing parameters like the rotation velocity, the initial velocity, that actually describe the whole bulk of mass coming towards the protostar. So one open question still is, where does the mass come from in both of these sources? In the case of PERM50, we see clear evidence that the streamer is larger from SMA data, where we have C18O outside of the primary beam of Noema. And if we look at older data from Hatchett et al., Hatchell et al. 2005, we see that there is a mass reservoir in between the filaments that we saw in this dense gas. So it is possible that the origin of the streamer is actually from here. Even in SMA, we look at it, it is longer. However, due to the lack of zero spacings in this data, we cannot make the direct connection. And the same happens with the case of IRS-1, where in ALMA, we only have 12-meter data observations. So we cannot make the larger scale connection directly from this HC3N data to the ALMA H2CO data. Nevertheless, the general direction of the gas flow at larger scale suggests that the IRS-1 gas from here is actually originated from this filament. But we need more data to confirm that. So here I leave you with my summary, and I want to highlight that ALMA has a high synergy with other observatories and gives access to vital scales for the study of streamers. So in PREM50, we find that it might produce an accretion burst in the future, and in B5, we're still analyzing the evidence of infalling gas. And I want to highlight that streamers are pretty long, but actually they can be much longer than what we can measure. So I would happily take your questions. Thank you.
Thank you very much for this wonderful talk, also highlighting the synergies. Elisabetta, do we have any
Not yet,
questions? No. Okay. I have a question. So you said earlier on, actually in the slide before, you mentioned that with ALMA there's only 12-meter data. Would you say that the compact array observations could help paint a fuller picture, or would you need even longer? Even larger scales?
I would say that we need both 7-meter and total power to actually get the full image of what's happening here. But already with 7-meter, we could extend the scales that we are seeing here to maybe connect this asymmetric infall to the condensations that we saw in dense gas in ammonia, because the image is actually like 1,000 AU scale, but if we have 7-meter data, we can actually connect with the edge or even half of these two condensations that are right here. But we would not get the total, without the total power, we wouldn't get really the full flux from both.
Yeah, I see. Elisabetta?
We have a question. Nice talk. How can a streamer form, and what are mechanisms to shape it? Turbulence, galactic rotation?
Well, for what I remember from simulations, there are several mechanisms that can actually form. First of all, they naturally appear with hydrodynamical simulations without magnetic fields. They already appear when star formation is clustered. So it can happen from flybys, for example. And if we include magnetic fields, they also appear from ideal and non-ideal MHD effects. So for example, we are still looking at how do they relate with the direction of the general magnetic field. And we see that they're generally perpendicular to it. So we are not really clear how magnetic fields would have a play on it, but they definitely do have a play on how the filaments arrange in the larger molecular cloud, so they can affect it that way.
Thank you.
Thank you. I don't see any other questions. If there are questions, well, you can either shout now or please write them in the Slack channel. Thank you very much, Teresa, for showing.
If you have time, we have another question. How long do these streamers last?
So
what is their lifetime?
Very rough estimates that they can be minimum of 9,000 years. For example, the one that I showed in PREM50, we estimate that its infall time is more or less 9,000 years. So we think that's like a lower limit to the life, and it could also be up to maybe the whole class 1 stage, which is around 100,000 years. So we haven't done a very statistical study of that because we do not have enough streamers observed, but we estimate that at the least it's 10,000 years and at the most 100,000. More than that, I cannot say.
Thank you.
Okay, thank you, Teresa, for your